Hello, everyone. My name is Dennis Kai from Alibaba Cloud. Currently, I lead the network infrastructure team. My team is responsible for the entire Alibaba network infrastructure, from the data center to the metro to the backbone edge, as well as the optical network and the DNS. Before I joined Alibaba, I worked for Cisco for many years, since year 2000. Based on the experience and the lessons which I learned from the last 2 decades, I strongly believe the two things play the most important role for the network technology evolutions. One is the scale. Scale does matter. The network value coming from the scale and the network complexity coming from scale as well. I really like the name for this event, Networking at Scale. And it's my great honor to give a talk at this event. The other thing is the network openness. The nature of a network is to interconnect among different parties. A network must be open and can interoperate with each other. The technology, no matter how good it is, if it is not open, in my opinion, it will be eventually left behind. So I'm a strong believer for open network. I often encourage my team to share our experience with network ecosystems. I believe our experience with large-scale deployment can help others, and we learn and benefit from others as well. In my talk, I will share some practical experience of how to build our predictable network. Hopefully, you can find something interesting to you. Let me introduce my company a little bit here. Alibaba started as a web company. Our company mission is to make it easy to do business anywhere. Certainly, this needs to be done through the digitalization, and we are the company who is helping our customer for digital transformation as well. On the right hand, as you can see, Alibaba have very broad business landscape, from e-commerce to the local consumer services to the digital media, entertainment, logistics, and etc. And all of these services are digitalized and running on top of the Alibaba Cloud. Here's the global infrastructure of Alibaba Cloud. Today, we have 28 regions, 85 availability zones, over 2,800 edge locations in 200 plus countries and regions. In the past 5 years, we made huge progress for our network infrastructure from many aspects: the scale, reliability, operation efficiency, etc. So I'm going to share some of our experience behind the scene in this talk. Before talking about our network, let's have a quick review of what happened in the last 2 decades and why we believe the network should evolve towards the predictable network. For the first 10 years of this century, people and companies just want to get connected. Internet is blooming. Network technologies had been evolved rapidly. There were lots of innovations and protocol standards coming out at that time. In fact, many of these protocols were invented to solve the interoperability issues between different vendors or between different generations of the network. Network become more and more complicated. The network device like routers and switches become more and more complicated as well. And the network device become a core competitiveness. I'm one of the such kind of engineer who made the routers, and we launched a very popular router called Cisco ASR 9000, and I was one of the founder engineers. If you work in this area, you probably know ASR 9000. ASR 9000 was such a big success, and I become one of the popular person in the field. And I got a chance to work with many Tier 1 service providers worldwide. Well, around 2012, I remember we started to work with Facebook, Google, AWS, those web companies. By the way, I was the person who installed the first Cisco router into a Facebook production network. It was one of the very early Facebook leased data center in Santa Clara. And that year, we also start to talk with Google, and Google said, hey, we are very interested in your ASR 9000, but can you support OpenFlow? And also, Google gave us two amazing numbers. One number is for 100 gig pricing point. They asked for $1,000, but our listing price is over $10,000 at that time. And also, they're asking for like tens of thousands of 100 gig port. this is unbelievable at that time for me. Well, that actually came into the second 10 years. It was the era of the web and the cloud. The web scale really drives the network architecture revolutions. The traditional network architecture products, operation, and cost, they just cannot support the web scale. The scale does matter. So we enter into SDN software-defined network, and we all know what happened. Automation, white box, open API, disaggregation, network virtualization, etc. Network was changed from the protocol-centric to the software-centric. Today, we can create a very big virtual network globally for our customer in the cloud in just hours, if not minutes. This is unbelievable 5 years ago. Today, our cloud network is very advanced already. It's very simple and elastic, and it can scale very well. Then, what should we focus in the next couple of years or 5 years? What's the trend for the network infrastructure? And what's the trend for the cloud computing? First, cloud is expanding from central to the edge. The cloud will become a public infrastructure to support the digital world, just like water, gas, those are public utilities. The new digital world infrastructure must be super reliable and secure, and must be cost and operation efficiency. And more important, it must be able to provide the predictable performance. Just like you turn on the switch light or turn on the faucet, you know what happened. This is we call predictable. Second, today data center network was built for traditional IT workload, and it can scale, but it just cannot scale well for the AI and machine learning workload. This will require high performance, predictable network to scale out the AI cluster. And the third, the big cloud company are building their own chip like CPU, GPU, and now the DPU and IPU. Given what we have now and what's happening for the future, we believe we should focus on building a network with predictable performance, which can work better for AI and machine learning workload, as well as for the fully distributed cloud computing as public infrastructure. Well, from the classic network to the SDN, it is a dramatic architecture change from the protocol-centric to the software-centric. But when we talk about the predictable network, it is from the user's point of view. It is not about the dramatic architecture change. It will still be built on top of the SDN framework. We can call it SDN+. But the focus will be shifting from the software to be software and hardware fusion or co-design. So we can take a full use of this advanced capability and programmability from those hardware chips to provide the predictable network performance. Well, how to build such kind of network? As you can see here, a cloud network can be divided into 3 domains: the big data centers and many small edge sites, and the global wide area network to interconnect them together. To build the predictable network as our goal, we have 2 systematic approaches. One is we call white box approach. The other is what we call host and network co-design systematic approach. White box is well known, but how to develop and deploy the white box? Different companies may have different approach. Our approach can be summarized using 3 words: single chip, single protocol, and programmability. Today, switch chip has a very high capacity. A single chip can support 256 100 port. Single chip box is well more simple than traditional chassis-based switches. We only build 2 switch SKU in our DC. One is for our TOR, the other is for the aggregation and the spine. Today, our DC network are 100% built with these 2 switches. And today, we are expanding the single chip white box approach to the one network. Well, the DC network and the switches are relatively simple, but the backbone network and the routers are well more complicated. There are a lot of legacy protocols, as you know, right? The MPLS, traffic engineering, VPNs, etc. Our idea is to simplify this first. We simplify and converge all the routing protocols to be IPv6 only and use SRv6 to provide the network functions. Well, simplicity is one of the most important reasons, but there are other considerations behind as well. As I said earlier, cloud is expanding from central location to be distributed. So for central cloud, we're talking about millions of servers in hundreds of locations. But with distributed edge cloud computing, it will be millions of the servers in the tens of thousands or even more edge locations. The wide area network domain is much bigger. So how to handle such big scale for the cross-domain traffic engineering and make our network foundation sustainable to be a public infrastructure? Another consideration is to provide fine granular service SLA. Our customer is very diverse. They have different requirements, and some of the requirements, some people may not understand is region specific. So for example, some of our customers and applications, they require the traffic go to a certain link when it across the countries, or go to a certain peering link, or go to certain service providers. How can we offer such fine granular service SLA? We conclude to go with segment routing v6 as our strategy for the one network evolution. The white box systematic approach can build up a simple and reliable network foundation, but it is not sufficient to provide the predictable network performance. It cannot meet the requirement for the AI and machine learning workload. It cannot meet the network quality requirement for our one network. So to solve this problem, we came out what we call host network co-design system, which I'm going to talk about in the next couple of slides. Here are the Sonic-based white boxes which we built in-house and deployed. For the DC, as said, is 100% white box. And we deployed 2 generations of the switches already, and we are working on the 3rd generation of the switch with 51.2 terabit chip. For the edge network, we use P4-based chip to build our hyper-converged network platform. And now we are spending a big effort on our one network. We developed routers and optical transport box based on the Sonic as well. Both of them are in the field trial right now. And for the peering router, we invented a system called EPF. It is made by a small class of the switches and with a server running the control plane. The data plane is based on a segment routing, and we can pre-build a backup path to mitigate different network failure scenarios. And this can reduce the network convergence 10 times better for many cases. For the optical transport white box, we developed a small form factor based on the Sonic as well. It can have multiple plug-in modules for both optical and electrical functions. In this box, the optical vendors provide us the API, and we build the Sonic system. And we plan to bring this to Sonic open community, and we're going to open source it. Today, AI, machine learning, and high-performance storage are really driving the data center network evolution. In the past 5 years, when we deploy the RDMA at large scale, we run into all kinds of performance issues. And we came out a bunch of new ideas. And with this new idea being implemented and deployed, today our data center network is getting very close to the predictable network performance as we want. The performance has been dramatically improved, especially for the tail latency and the failure recovery time. And today, we deployed a large-scale GPU cluster without much of the performance degradation. In other words, the computing processing power can increase linearly when the GPU cluster scale out. So how can we achieve this? This is due to our host network co-design systematic approach, as I mentioned. We call this a pretty fabric. So let me go through this with 3 tiers from the bottom to up. At the very bottom, we built a very solid network foundation with white boxes. As I mentioned, it's based on a single chip, 3-tier class topology. For any server-to-server communication, it is a maximum 5 hops away. Network latency has been optimized. And more important, when we choose a switch chip, we choose the one which has advanced data plan programmability as our TOR. So we can leverage this advanced chip capability to provide some network telemetry in real time to the server side. So then it come out to the second tier. We call it edge and core co-design. Edge here means the server and the NIC, and core here means the switch network. It is a co-design between the server and the switch. The initial idea comes from the server dual homing solution. So we invented a new but a much simpler multi-chassis lag solution where the server NIC and the switch work together instead of two switches, working together, try to sync up the data running protocol between each other. That's the traditional multi-chassis lag. For the traditional multi-chassis lag, we often run into the split paradigm issues. With a new approach, so it's running very reliable in our network. So later on, we continue this idea to the congestion control. We invented the HPCC congestion control. The idea is also very simple. We use inbound network telemetry to get a critical switch data plan running status, such as the queue length, port usage, and so on, and give this information to the server. So the server will have much better understanding of what happened in the network, and it can do much better congestion control. And then we apply the same idea to the multi-path support. Today in the data center, there are lots of ECMP paths, but the average link usage is very low. Typically, it's only like in the range of 10 to 30% in our data center. However, there are lots of microburst and heavy links, which could cause high tail latency. With this edge core co-design, for our critical applications, we can have predefined disjointed network paths, and the application can monitor the paths in real time and take action accordingly. And some of these ideas have been published into the UFabric in this year's SIGCOMM. Well, the server NIC and the switch co-design is still in the scope of the network space, which is still not sufficient. So here comes out the top tier, which we call it application and network co-design. So when we deploy the Rocky RDMA, we were thinking, how can we combine the Rocky network protocol with storage and AI applications to enhance the RDMA performance, such as for better scale, for multipath support, and for more efficient packet retransmission and congestion control. We came out with the SOLA protocol. SOLA is a UDP-based network protocol. It is built on top of the Rocky for high-performance networking. SOLA uses a reliable data graph for simplicity and for high scale. And also in this design, we make each network packet as one of the self-contained storage data block. This simple idea can dramatically reduce the complexity and improve the performance, and for much simple multipath support. SOLA is also applied to our AI applications as well. As a short summary here, with what we call host network co-design systematic approach, we invented quite a few ideas. And those ideas have been deployed, and today our data center network is getting very close to the predictable network as our vision. As I mentioned earlier, we are in the process of building a simple network foundation for our WAN network with a white box, and also with SRv6 end-to-end, due to a couple of considerations behind. One for simplicity, second for scalable for the distributed cloud, and the third for the fine granular service control. But during the real deployment, we found it is much more difficulty. The biggest challenge is how to work with existing network. How can we migrate the existing network to be SRv6? It is not easy. We came out some practical solutions, which I would like to share here. And for those who are deploying SRv6, hopefully it's something useful for you. First, let me describe the overall of a host network co-design framework for a predictable WAN. The basic idea is to have SRv6 end-to-end. The edge here means the host or the network device which does the SRv6 encap and decap. The edge node will register with our global service center and apply for SRv6 service ID. Then it does SRv6 encapsulation. With the SRv6 packet ending into our backbone network, the service anchor point router, typically is our PE router, will put the packet into the certain segment routing tunnels, which could have very fine granular path control. That's the basic idea. Next, let me explain how do we deploy this SRv6 edge node. If you look at the picture here, at the bottom is the Alibaba network, and the top is the public internet. In the Alibaba network, in the data center, we have the managed endpoints, and we have three kind of scenarios for the edge node. One is the server, such as our storage OSS server, and the second is for the switch for some of our edge locations. But for many existing scenarios, we don't want to touch the existing setup. Instead, we introduce a GSW, which we call it Global Service Switch. The GSW will work as SRv6 edge node. Well, that's for the managed endpoint. For the unmanaged endpoint, it will be aggregated into our POP sites from public access network. For regional POP, we also introduced a dedicated GSW. For small POP, we just use the server for the aggregation. So after the packet is SRv6 encapped, it will enter into our backbone network, where the service router will serve as a service anchor point, and the packet will be routed through certain tunnel based on segment routing SID. This is overall what we call edge core co-design for end-to-end service architecture. Well, besides that, I would also like to mention two things here to build our predictable WAN. One is for the global network quality management systems. We call it a cloud speed. We have deployed this over tens of millions of the endpoints on the app, and also we deploy this on the thousands of locations, and we can create a real-time network topology for the performance, and can feed this back into our network orchestration systems. The second piece is our X-Link systems. It is built to improve the quality for the last mile. We install the X-Link SDK into the unmanaged endpoints, and it can help monitor the network quality and performance over multiple public access which could be different service providers' wireless or Wi-Fi network, and choose the right aggregation POP site. And meanwhile, it can also multiplexing the packet over multiple paths. X-Link uses a multipath QUIC for the transport protocol, which we already contributed this to the IETF standard. Well, this is the framework for our predictable WAN, but if we zoom into the backbone network, it's much more complicated. The biggest challenge is how to migrate the existing MPLS-based segment routing to be SRv6. We have two backbones. The existing backbone, we call it AGN. The new backbone, we call it eCore. eCore will be eventually built based on a white box segment routing v6 end-to-end. Our strategy is to have eCore gradually take over the major traffic and leave the AGN not touched. Now for the eCore deployment, we came out with one creative idea. We call it hybrid traffic engineering architecture. Well, we have a service router deployed SRv6 and keep existing core routers continue running MPLS segment routing. But eventually, they can be upgraded to segment routing v6. I won't go through the details of this picture, but you can see here the green color service router or peering router will do the end-to-end SRv6 traffic engineering tunnels. But for the middle core routers, they can continue existing MPLS segment routing, but with some additional functions. We call it SRv6 Lite, where it can understand SRv6 header to get the service SLA information and route the traffic into the certain MPLS TE tunnel. Due to limited time, I want to be able to talk about our hyper-converged edge gateway platform. I just leave this slide here for you as a reference. Last but not least, we are actively contributing the open source community. We are one of the 7 initial board members for the Sonic project in the Linux Foundation. Sonic has become the de facto standard for the network OS, and the SI provides the ASIC level abstraction so the switch vendors can choose a different switch ASIC. And we initialized the S3IP project. This is based on our experience of developing and testing ODM-based white box. The S3IP, we open source it and make it an open standard for the hardware spec, and also we define the testing framework, which will make it much easier for the ODM vendors. We plan to bring S3IP into the Sonic community as well. We are also working with the Sonic Technical Steering Committee to create SRv6 working project to open source our SRv6 code. Due to limited time, I will not go through the details here. As a short summary, in my talk, I shared our 2 systematic approaches of how to build a predictable network infrastructure. One is the white box approach. We deployed Sonic-based white box using a single switch chip from the data center to the edge and now to the backbone and optical transport network. The other is what we called edge network co-design systematic approach. And we use this to build our predictable data center fabric network already. And we are in the process of building SRv6 based network for our predictable wide area network. Well, that concludes my talk. Hopefully, our experience could be something helpful for your network design. Thank you for your listening.